Okay, here's a What the Physics video with rotational stuff. We're just trying to wrap it up. We're going to be talking about rotational momentum and rotational kinetic energy. So as I've said before, the easiest way to think in terms of rotational or angular stuff, it's kind of interchangeable as far as I understand. The easiest way to deal with that is thinking of it in terms of linear or translational stuff and then seeing what we can do. We already mentioned the whole business about turning Greek letters into Roman letters or Roman letters into Greek letters by simply multiplying or dividing by the radius. Cool. Unfortunately, and I have no idea why, we're no longer using Greek letters to demonstrate angular stuff. But the concept there is still pretty easy. We know about linear or translational momentum, P is equal to mv. The rotational version of this is going to be L equals I omega. You say, all right, cool. I've got the I, we talked about that before. That's the what? Moment of inertia, right. You remember all those hilarious puns are coming back to us, right? No. Nightmares. Okay, and the omega is angular velocity, right. Okay. Why are we using L? No idea. Just like with P, I have no idea why we use P for momentum. No idea why we use L for angular, whatever. Okay? But we can still come up with some easy comparisons. Okay? We've got F delta T, M delta V, and just plain delta P. That's all for linear stuff, right? We can go ahead and extend that onto rotational stuff. We know the rotational version of force is going to be torque. So that's going to be torque times delta T. It's kind of amusing because they're both T, but one is Greek. And then it's M, instead of M for mass or inertial mass, it's the rotational inertia. So that's going to be I, and then the delta V is delta omega, and delta P, well, that's going to be delta L. So you say, oh, that's a whole lot of stuff to remember, folks. Sure. But if you're thinking in terms of the linear stuff, it's really not that bad. Okay, and why bother stopping there? We're also going to talk about conservation of angular momentum. Now, conservation of angular momentum is kind of different from conservation of linear momentum. With linear momentum, we were talking about two or more objects running into each other. We'd say, oh, the momentum before is equal to the momentum afterwards, and some of the momentum transferred from one object to another, and stuff like that, yeah? It's not quite the same thing here. We're not going to talk about things that are spinning around and somehow transferring angular momentum from one to another. Instead, we're going to be focusing on one object and how its angular momentum might change, assuming we're in a closed and isolated system. That means no net torque. That means angular momentum, the total angular momentum is going to be conserved. So in this case, if we can see it as momentum is I times omega, we're going to have our initial values and our final values. If we're going to change the I, if we're going to increase the I, we're going to decrease the omega, right? How might we increase or decrease, for that matter, the I? What is I? What is the equation for I? Do we recall? It does depend on the shape. Absolutely true. However, the whole depends on the shape. That only really counts for the little digit in the front. Okay, so There might be a 1 or a 1/2 or a 2/5 or a 42 over 6,000, which does not exist, or whatever. But then after that, you multiply it by m times r squared, or in some cases m times l squared, but we see that's effectively the same thing. Okay. In fact, some textbooks just say it's constant times mr squared. Some folks use like a k for a constant. I don't want to use a k because we've used k for constant all over the place. And we're about to talk about rotational kinetic energy, and that's big K, and that would just be too easy to confuse. So if you'd like to think of it as there's a constant times mr squared, go ahead and just use the constant c. Okay, so that c could equal 1, 1/2, and the various other fractions, right? 1/12 was in there, right? But the point is, there's m and there's r in moment of inertia. Are we likely to be changing our mass? I mean, technically, well, let's not even bother with that. We're going to be focusing on changing our radius. Okay, so if we increase the moment of inertia, then we're going to decrease the angular velocity. Okay, and pretty much what we're talking about is moving in versus moving out. So, click. Okay, so these are some of the pictures from the textbook. We've got a figure skater spinning around and moving arms in, moving arms out. Is anyone in here into skating at all? Skating, or whether it's ice skating or even rollerblade, or dance for that matter too. Okay, I'm not asking for names, but what can you say about it? You raised up your hand so you could say that you hate it. I asked if you were into skating or dance, and you took this moment as an opportunity to rag on the sport. That's wonderful. Thank you. Let's say one of those other people that was raising their hand, and please don't go in the same direction as we just saw. Sir. You hate it also? No? Okay. Do you have any do you have any experience with it maybe? Okay. Go on. Yes, you have some experience. Go ahead. Well, I'm going to be talking about the physics, but I'm just wondering if you can say, like, yeah, I've noticed when, so on. Perhaps you're not the best person. Okay, well, there were some other eager people, but maybe it's all downhill from here. Okay, well, okay, yes.
Like, when you're skating...
When you're skating?
It's easier, like, if you're, I don't know, like, turning around or something like that, it's easier if you're going, I don't know, if you're going, like, slow, you kind of have to balance yourself.
If you're going slowly, like on a straightaway type thing, or when you're turning?
Not when you're turning.
Okay, so just on a straightaway.
Yeah.
When you're skating, it's easier, what?
Kind of, like, you have to kind of balance yourself, like, everywhere.
Okay, so that's kind of along the lines of just playing moment of inertia.
Yeah.
Okay.
And if you're going fast, you kind of have to bring yourself together.
Okay, so if you're going faster, you kind of need to compact yourself, is that?
Yeah. Like,
Okay.
you don't have to be spread out if you're going fast. Like, you don't have to. It's easier to. I don't know how to explain it.
Okay. Let the record show that the person speaking now has moved her arms up and down to help us understand. But I'm not sure. I'm sorry. I'm just not able to interpret what you're saying. I'm sure you have more experience with skating than I do. I have skated like a couple times in my life, and I fall, and then it's very sad and embarrassing. So, okay, maybe not even first-hand experience skating or dancing or whatever, but wait a minute. You dance, right?
Yeah.
Ah, there we go. Aha. What can we say about this? Okay, hold on. Let me describe that in words. Okay, so our dancer is saying that when you're turning, you have to have your arms in a certain position, and you were saying like making a circle in front of you, like you're hugging someone, right? I'm sorry, like hugging a beach ball. Okay, and go ahead. Okay, when you're turning, you have to keep your arms close. Okay, and why is that? Okay, so you're able to turn faster if your arms are closer in. So if you're hugging a smaller sized beach ball, perhaps. If you're hugging a larger sized beach ball, or you just had your arms straight out from your sides, that would make it not so easy to turn, right? Okay, good. That's the type of thing I was hoping for. Just like, yeah, I notice when I ice skate, or perhaps when I've seen ice skating on TV or something. Mrs. Fair loves ice skating when it comes to the Olympics. I'm just like, oh, okay. This is yeah. The extent that I'll watch is if Blades of Glory comes on, I'll watch that. But um, I never really broke its visuals down in terms of physics. Maybe they got it right, maybe not. But yes, what you're saying in terms of dance certainly applies to what we're saying in terms of ice skating. If we have our body extended outwards, we have a lot larger moment of inertia, and that means it's going to be harder for us to spin. In this class, I believe last time, I had taken this umbrella and let the record show I have an umbrella in my hand. And if I were to um, make the umbrella longer, it's still the same. I can still spin it just as easily. If I were to open up the umbrella, okay, it's now harder for it to spin because the moment of inertia is larger. That's exactly what we're talking about with the ice skaters. So we say, cool, Fair, I understand moment of inertia, or at least reasonably well. But what are you talking about with this whole angular momentum conservation biz? A skater can be twirling around or spinning around like this, and then move his or her arms in closer and closer, and because angular momentum is conserved, their angular speed is going to go faster and faster. So they twirl really fast. If you're twirling really fast and you want to come to a finish, dancer, what are you going to do? If you're spinning around really fast and you want to slow yourself down, you would put your arms out. Yes? Yes. Okay. Um, Something that I had heard, like some type of interview about, I believe it was about ice skating, but I'm assuming it might apply for dancing as well. They said, "Oh, what is the area of your body that you have to work out the most?" Because most people would figure it's going to be your legs because you're just moving around so fast and such. But this person said, actually, it's your arms because you have to control them so exactly. You can't just let them flop in or flop out because they're controlling the speed. Do you think that's similar? You agree? Okay, cool. Yes.
Wouldn't it also be the core?
I would say so as well, because it all comes from there. But I was just kind of surprised with the arms comment because I figure you're not really using your arms unless maybe you're in pairs or something and you're lifting someone up. So that was a big surprise. So I just thought that was cool. Something else, if you actually watch ice skating or as well as dancing, if they are spinning, it's not simply them moving their arms out to slow them down. They also typically would move out one of their legs. Okay, why do you think that is? anyone. This is not a. It has to do with angular and torque and stuff. It's not a rhetorical question. Rhetorical. Okay. All right, stop that. So there's a hand. Yes.
Is it because like what you said with the umbrella, like it'd be harder for them to like they'll slow down if they spread them.
Right. Okay. So they're just spreading out as much as possible. If you think of it in terms of, well, their legs are going to be longer than their arms, at least for the average person. And also, at least for the average person, your legs are more massive than your arms. Now, you're not going to spread out both your legs because then you'd be flying. So that'd be kind of cool. But that's a whole different competition you got going there. In this case, we're just saying, like, you put out one leg to slow yourself down. That helps just like the arms. Speaking of increasing the mass to have us slow down, we have this this thing going on here where someone can spin around and make themselves go faster or slower.
What's that?
Okay, so how often is it that you might be sitting on some type of spinning chair and with barbells in your arms and just like, hey, let's do this, right? But if you were to be spinning around, you move your arms out, you are going to start spinning slower and slower than you were before. Now, why is it that they're showing this with the barbells? What's that? Mass specifically, not simply weight, but the mass because of the rotational. Right. Okay, so you imagine if you're just standing there. Okay, so I'm just standing here. You imagine I am like a disc or cylinder. And you say, oh, well, I can figure out what my moment of inertia is going to be. It's that of a cylinder, right? And, you know, you could estimate the radius and so on. And am I evenly distributing my mass? Of course not. But let's just pretend. What happens when I put my arms out like so? If I make a T? Well, my torso area, the cylinder hasn't changed much. Technically, it has lost mass. But by putting my arms out, I am adding on another moment of inertia, which would be like the long, thin cylinder, right? Okay. If I add on the mass, the barbells at the end, what would that be? Just additional masses. That's the whole mr squared business. Okay. So by having them out there and my arms, I'm just adding on all these moments of inertia. So it's getting larger and larger. That's why the rotational velocity is going to be smaller. But notice this whole time, we're not talking about including any external forces, so there's no net torques going on. Kind of hard to do this demonstration. First of all, well, I've seen students like spin right off before, so that's kind of fun. I mean, exciting. I mean, well, you get safety goggles, so it's okay. No, usually, as soon as you start to fall, people just usually step off of the platform one that we have. And but more importantly, there's the issue of friction. Friction would be an outside torque that would kind of mess things up. Okay, there's this puck on a string example. I'll have you do that on your own. I just got it from the textbook, so this slide shows the information. You can also get it from the textbook too. Astronomical applications. The textbook, speaking of, it referenced a collapsing star is going to shrink down its radius. Anyone into astronomy type stuff? I think it's really cool. Okay, so we know that stars have a life cycle. It's kind of weird to say a life cycle because we wouldn't say a star is alive, but We say star is born, it ages, and it putters out and dies, right? And what happens to it in its life cycle depends upon its mass, and but what they're getting at here is when the star begins to collapse, it's going to reduce its moment of inertia. Why? If the star gets smaller, what's happening to it? Yes? The radius is decreasing, right. Now, technically, is this all right, so yes, the radius is decreasing. The textbook doesn't actually address how it also loses mass and stuff like that. They're just assuming that it's a constant mass just for simplicity. But technically, it will be losing mass in the process. But yeah, with the smaller moments of inertia, the angular velocity will get larger and larger. Okay, so that means it will be spinning that much faster and faster. Now, depending on the size of the star, like if it turned into a white dwarf, we wouldn't really be able to see it. And those don't usually spin that fast anyhow. What I'm talking about with fast spins would be this guy here, a pulsar. Okay, and this is supposed to be an artist's rendition, I guess, of a pulsar. So it's spinning around very, very fast, and it's sending out signals on the textbook reference on the order of, like, the first one noticed was about period was like 1.3 seconds. So that's how long it takes a star to spin around. So it's going very, very fast. Okay, and of course the period would depend on any number of things. But if we can get a star to spin around in about 1 second, yeah, that's Hall. Some other application-y type stuff for astronomy was if you were into like the solar system type stuff, you've probably seen that all the planets are orbiting around in the same direction, right? So if you were to look from here, they're all spinning around like this, yes? It depends on if you're looking from the top or the bottom, if it's clockwise or counterclockwise. But the point is, they're all going in the same orbital direction. Most moons, not all, but most moons are doing the same thing. And in fact, most planets are spinning in that same direction. There are some exceptions. Venus actually has a retrograde spin. No one really knows why. And Uranus is actually kind of tilted so much it's more like it's on its side. So that's just a weird one. But even if we're talking about like asteroids and stuff, they're all going around in that same direction. That has to do with conservation of angular momentum. And when the whole solar system was originally born, I mean, it was just a whole bunch of dust, clouds, and rocks and stuff. And it was just spinning in this one direction. So you'd say, well, why would it start to spin in another direction? It's not that it doesn't happen. It's just not. It's not going to continue to happen very long. For example, Mars has 2 moons. Okay, Mars is, those are the moons closest to the Earth, other than, of course, our own Luna. Its 2 moons are Phobos and Deimos, which means fear and panic, which goes along with the whole Mars is the god of war, and he brings with him fear and panic to the battlefield. Kind of cool. Anyhow, they're spinning in the what we'd consider the opposite direction. They have a retrograde. I'm sorry, not spinning. Orbiting in a retrograde direction. We know that they are captured moons. We say that they are captured as in they were just some giant rocks zooming by, and they got close enough to Mars that they were pulled into its gravitational field into a relatively stable orbit. I say relatively stable because eventually, because they're fighting against Mars's angular momentum and the gravitational stuff, that they will eventually spiral in and crash into Mars. I'm not saying it'll happen tomorrow or even in the next 100 years, but it will happen. So we know that they're captured because they wouldn't still be doing that if they were formed with the rest of the solar system like 5 billion years ago. So that's kind of cool. Rotational kinetic energy. You didn't think we forgot that one, right? We've got rotational everything else. We're going to apply it here. We've even got rotational work, if you want to think about it that way. We're not going to focus too much on that, but rotational work would just be take out force and put in force. Okay, so rotational kinetic energy is most noticeable if we recall back to earlier on in the year when we were doing projectile motion, and I say we've got a ruler and we've got a ball going down the ruler. And I said, oh, I can calculate how fast the ball is going to be going if I just knew the height of the ruler, or the height of the incline, I guess, from wherever it started. And I said, it's not quite exact because there's a little bit more to it, and I just kind of mentioned it at the time. So here's when we're going to clean that up. Okay, you might say, oh, it's going to change all of its gravitational potential energy into kinetic energy. And I can just use mgh is equal to 1/2 mv squared, cancel out the masses, easy to solve for the final rolling velocity, right? No. Point is, I just said rolling velocity. If this were like a skier skiing down a frictionless hill, then yes, that would work. But if we're talking about a ball rolling down this hill, rolling is the important term here, that is not going to work because some of the energy is going to go into the translational motion, but some of it will also go into the rotational motion. Okay, and this just aside, it probably doesn't really matter that much, but I did say it's a frictionless hill. If it were frictionless, then the ball actually wouldn't roll, so that's a whole different thing. But we're assuming we're talking about a ball with rotational kinetic energy. So we've got U, gravitational potential, and then translational plus rotational kinetic energy. So, simplify that, we call it K-Rot. Sounds like a DJ name, I don't know. DJ Physics, DJ K-Rod, I don't know. Yes, thank you. All right. We're talking about rotational inertia, just like before, and the equation for translational kinetic energy is 1/2 mv squared. Stands to reason we can do this same biz right here. Typically, we're going to be talking about a solid sphere, like a ball, or I guess that could be a hollow sphere too, depends on the ball, or like a cylinder or something, but it can apply to a number of these different things. What I'm pointing out right here is, you see this 0.5, right? The 1/2 that goes in front, that is different, that is totally separate from the constant c in front of the mr squared. So if you've already got a 1/2 in front of your mr squared, when you plug that in here, don't forget this 1/2. Okay, if you've got a 1 for the other one, don't forget this 1/2. So you'll have two fractions in the front. Okay. I mentioned the whole sliding down the ramp, and we could easily do a calculation. Next time, I hope that we'll be able to do a similar activity with, say, like a Matchbox car. Say, like, oh, if I've got this loop-de-loop set up, where can I start this to make it go all the way around the loop? And you say, oh, I can do that. I'll use conservation of energy, just regular kinetic and gravitational, and I'll use circular motion, because I got to figure out the speed at the very top, right? That shouldn't be too difficult. And that should work for a Matchbox car, but it won't necessarily, or it won't work for, say, a marble. Okay, and hopefully we'll see why that is. Okay, and then we'll also have this cool activity called the Great Soup Race, where we're going to race cans of chicken something, chicken, cream of chicken, chicken noodle, and chicken broth down inclines. And you say, wow, that sounds like a lot of fun, Fair. It is. It is. No, because it's actually quite surprising what happens. But you'll have to wait on that because it's super cool. But you'll have to wait. Questions? Delish. Physics.